Hi, and welcome to this section where we're going to continue with our study of the complex variable analysis, and in particular we'd like to look at the Cauchy-Riemann relation. So previously we had our function here, a complex valued function f of z equal to z cubed, and when for z equal to x plus iy, which we wrote as this, okay, after expanding it, we saw that this function here was holomorphic, i.e. it was differentiable, okay, while the function f of z, which was given as 2y plus ix, was not holomorphic, because we found out that as delta z approaches 0 along a direction which is parallel to the real axis, in that case only delta x was varying, only x was varying, and delta y was 0, okay, we found that the limit, when we considered in this direction, as we approached z in this direction here, was different from that when we approached z, i.e. delta z approaching 0, along the direction which was parallel to the imaginary axis. In other words, only delta y was varying, only y was varying, and the change in x was 0. So we found those limits to be different, okay. One was I, another one, anyway, I don't remember, but you have the video, just the previous video. So then we concluded that this function here was not holomorphic, and it was important to know that it was not holomorphic, i.e. not differentiable in the sense of complex differentiation. Yet it was made up of two functions, 2y and x, which, if we are considering real valued functions, are differentiable. And yet, if now it becomes a complex valued function, i.e. a sum of the real and the imaginary, we see that it is not differentiable. So the question would be now is that why was our function like why was the function like f of z equals to z cubed, why was it holomorphic? Okay, why was it holomorphic? Yet the other function here, f of z given as 2y plus ix, why was it not holomorphic? Okay, so that would be the question here. So the answer, okay, the answer lies in a certain relationship between the answer lies in a certain relationship between the real and imaginary values, okay, and this relationship is given by the Cauchy-Riemann relation, okay. So the answer why one would be holomorphic and the other would not is just in the relationship between the real and the imaginary values, and this relationship can be deduced through the Cauchy-Riemann relation. Okay, let's see. Let's write down something here. So we are going to write down a theorem here. Okay. So what was this theorem say? It says that if f of z, okay, which is given by a sum of the real and imaginary, it is complex valued function, if f of z, okay, is holomorphic in a region R, if it is holomorphic in a region R, then U and V satisfy one, that the partial derivative of U with respect to x should be equal to the partial derivative of V with respect to y, okay, And then the second condition is that the partial derivative of u with respect to y should be equal to negative partial derivative of v with respect to x. So these two conditions are satisfied in the region R. Okay, so this is what we call our, this here is what we call this is the Cauchy-Riemann relation, but in this case it is called a necessary relation. Okay, that is just the necessary here, the Cauchy-Riemann relation. Okay, so we would have to write it down in a, if we want, the sufficient, okay, the much stronger condition here, we would have a number of, okay, let me just write it down and then we see. If the following conditions are met, if the following conditions are met in region R of the complex plane, okay, if the following conditions are met in the region of the region R of the complex plane. Okay, so what are those relations? The very first one, the necessary conditions, which we wrote down, that partial u partial x equals to partial v partial y, and partial u partial y equals to negative partial v partial x. Okay, no, sorry, before we get to this is one of the very last one. Sorry about that, I bungled the order. Well, this one also is there, but it's not the order. Before even we go to this, before we go to compute the derivatives here, we first have to show, or we first have to say that the partial derivatives themselves, that the partial derivative of v with respect to x and the partial derivative of u with respect to y, the ones we are going to use in the necessary conditions, and then the partial derivative of v with respect to x, and the partial derivative of v with respect, is it v with respect to x? It is u with respect to x. Okay, and v with respect to y will first excuse me they have to exist. That is the first thing. Okay, now after existing, all of them, again the same partial derivatives, have to be continuous. Okay, first they exist, 2 they are continuous, and then 3, these ones here satisfy, okay, the Cauchy, these satisfy the Cauchy Riemann. Now this is our necessary condition. The necessary condition, we are going to say that these same partial derivatives here satisfy the Cauchy Riemann relation. I'll just write it down again, just so that these things can stick further. They satisfy the Cauchy Riemann relation in R. Okay, so I'll just write it down again so that it can stick. And what was that? First, we say that the partial derivative of u with respect to x should be equal to the partial derivative of a with respect to y. Okay, and the partial derivative of u, okay, you can always go in that order. First u with respect to x, v with respect to y, then u with respect to y should be equal to the negative partial derivative of v with now respect to x. I hope it's pretty easy to remember. So this is now a much stronger condition, which we are going to call the sufficient condition. The Cauchy-Riemann relation here, the Cauchy-Riemann relation here is Cauchy Riemann relation is just necessary. Okay, so that's it, that if f of z given as that is homomorphic in region R, then u and v satisfy, you know, these equations here, this relationship rather. And if you know, now go for the much stronger condition. Okay, first the partial derivative exists, next they are continuous, and thirdly the same partial derivatives satisfy, okay, the Cauchy-Riemann relation given by these equations. Okay, so now let us look at an example here. Okay, let us look at an example. Alright, oh, do we look at an example? No, we can verify the ones which had actually. So we had f of z given as z cubed, of course for z x plus iy. Okay, so we had this as written as that minus 3xy squared, okay, plus 3x squared y minus y cubed I. Okay, so yes, so we have this as our u of xy, and we have this as our v of xy. So all we need to do is, one, do the partial derivative exists. One, I think yes, we can always say that the partial derivative of u with respect to y, okay, and then the partial derivative of v with respect to x, and then the partial derivative of u with respect to y, and the partial derivative of v with respect to y are, okay, exists and are continuous, because, okay, now this goes back to our calculus which did differential and integral calculus, because u of xy and v of xy are polynomials. Okay, so we can easily see that these are polynomials. This is a polynomial, okay, and this is a what? A polynomial, you can see. Okay, so and what is the reason? Why are we just stating that? Because we know, okay, from our calculus, I hope you remember this, that all polynomials, okay, are okay, all polynomials, their derivatives, okay, their derivatives exist and are continuous. Okay, all polynomials have their their derivative exists and are continuous. So in essence, condition 1 and 2 is already met. That one, the polynomials, the derivative exists, and 2, they are continuous. So next is just for us to verify that they satisfy the Cauchy-Riemann relation. 1, we find the partial derivative of u with respect to x. Okay, I bungled the order here. The partial derivative of u with respect to x, do I have it here? Yes, and then the partial derivative of u. Okay, the order doesn't matter here, but it's the same, which I'll need to compute. So the partial derivative of u with respect to x here should be equal to the partial derivative of v with respect to y. So the partial derivative of u with respect to x is equal to 3x squared. We are differentiating u. Where's u? Where's u? This one here, with respect to x. Okay, so x is the variable with which we are differentiating respect to, but y is considered as a constant. Okay, so it is simply going to be this one here, 3x squared minus 3y squared, okay, because y is a constant here. So we have 3x squared minus 3y squared. Then next we have the partial derivative of v with respect to y. So you look at v here. Now with respect to y, x is a constant, y is the variable. So when you differentiate the first one with respect to y, all of this is a constant. So I have 3x squared, then minus y cubed with respect to y is 3y squared. So we have 3x squared minus 3y squared. So I hope you can see that the first condition here is already met, that the partial derivative of u with respect to x, I'll just color it here in the same code. The partial derivative of u with respect to x equals to the partial derivative of v with respect to y. Okay, so next condition here for our Cauchy-Riemann relation would be, now we want to find the partial derivative of u with respect to y. Okay, so the partial derivative, okay, I'll put it here, the partial derivative of u with respect to y. Now we can go back here. Where is u? Here is u. Now with respect to y, y is the variable, x is the constant. I have a feeling, haven't we computed this before? U with respect to y. No, it's okay. So y is the variable and x is the constant. So when we differentiate this one here, since x is the constant, when we differentiate with respect to y, that is 0. Okay, then with respect to y, we are simply going to get 6xy, negative 6xy. We should not forget the negative here. Alright guys, so we have negative 6xy minus 6xy. Okay, then next, the partial derivative of v with respect to x. So we come here, where is v? Here is v. Now with respect to x, okay, y is a constant, so that is going to be 0, and then with respect to x, we are going to multiply, drop the power here, so you have 6xy. So what do we have? We have 6xy, and clearly you can see that these two here, okay, satisfy our second condition here, which I'm also going to highlight in yellow, that the partial derivative of u with respect to y and the partial derivative of v with respect to x are negatives of each other. Okay, the partial derivative of u with respect to y and the partial derivative of v with respect to x are negatives of each other. Okay, so now that is why after all those are met, then we can say that therefore our function f of z, which is given as z cubed, is holomorphic. Okay, so I will leave it for you as a task, okay, to use the exact ones and then show that our function f of z, which was given by 2y plus ix, is not holomorphic. Okay, remember we have said that if they are holomorphic, one, we are going to check that the partial derivatives exist. Next, that those partial derivatives are continuous, and thirdly, that they satisfy, okay, the Cauchy-Riemann relation. Okay, all of these have to be satisfied. It can satisfy that, and fail at any one of those. In other words, it has to satisfy all of them. It fails at any one of them, then we are going to say that it is not holomorphic. Okay, yeah, so yeah, I don't know if we have more time. I don't want to make the video so long, but I think we have some more time. A few minutes. Let me take just a few more minutes, and then we look at just one or two more theorems here. So we shall say some important theorems that we are likely to encounter. Okay, one theorem, we are going to say that if f of z is holomorphic, okay, if it is holomorphic, in a region R, okay, if it is holomorphic in a region R of the complex plane, then it has derivatives of all orders at all points in R. Okay, so if a complex variable function f of z is holomorphic in a region R of the complex plane, then it has derivatives of all orders at all points in R, i.e. it is infinitely differentiable. You can differentiate it first time, second time, third time, fourth time, and so on. Infinitely differentiable. Okay, that is what the theorem is telling us. Pretty powerful. If it is holomorphic in a region R, then the derivatives of all the orders there exist. Okay, right, let us look at another theorem here. So what does this other theorem here tell us? If f of z is holomorphic in R, okay, so we can say that if f of z is holomorphic in R, or in a region R, whatever, then it can be expanded as a Taylor series. Then it can be expanded as a Taylor series. It can be expanded as a Taylor series, okay, around any point z0 in R. So what are they saying here? If f of z is holomorphic in R, then it can be expanded as a Taylor series expansion, around any point z0 in R. Okay, so I hope again you remember our Taylor series expansions from around I'm not sure where, in which course you did this, but it's assumed for now we know our Taylor series expansions here. So what do we want to note? That if we want to write a Taylor series expansion if we want to write a Taylor series, okay, for a function of a single variable, then that function needs to be infinitely differentiable about the point where you're expanding. Okay, so how do I make this easier? No, but I think it's just saying exactly the same thing which I've said here. Okay, let me just write it down. If one wants, okay, if you want, okay, to write a Taylor series expansion, okay, for a function of a single variable. Please note we are just saying any function, a function, okay, not necessarily vector valued. So if you want to write a Taylor series for a function of a single variable, okay, that function, okay, has to be infinitely differentiable. Okay, it has to be infinitely differentiable about the point where you're expanding, i.e. z0. So look at the previous theorem. The theorem told us that if f of z is holomorphic in R, then it can be expanded as a Taylor series around any point in R. Okay, Maybe that is important because they have told us that so the note here is telling us that whenever I want to write a Taylor series expansion, okay, then wherever we are going to write the Taylor series expansion, the function has to be infinitely differentiable along that point. However, they have told us that if it is holomorphic, then it is infinitely differentiable at any point, okay? That means that we can have a Taylor series expansion for a function which is holomorphic at any point, okay? Because if it is holomorphic, you know, it is differentiable, infinitely differentiable at any point. Actually, the theorem here in this color, is it orange or what, which says that if a function is holomorphic in the complex plane, then it is infinitely differentiable. Then next they tell us that, hey, if it is infinitely it is infinitely differentiable, because you know holomorphic implies it is infinitely differentiable. Next, if it is infinitely differentiable, then you can expand it as a Taylor series expansion along any point z0. And then the note is just trying to remind us that whenever you want to write a Taylor series expansion, then the function has to be infinitely differentiable at that point. Good enough, we know that it is a holomorphic, therefore it is infinitely differentiable at any point we are going to choose. All right, okay. What should we say? Okay, let me just give this simple illustration here before I go further. So, e.g., if you have our function f of z equal to 1 over z, okay? So, we know that this function here is not defined at z equals to 0, okay? It is not defined at z equals to 0. So let us say that we have our region of what? Okay, it is not okay. Let us say at that point there it is not defined here. This is z, okay. The point where it is not defined here, I hope you remember from your calculus, we say that it is a singular point. That is a singular point, okay. We cannot even differentiate it at that point z equals to 0 because of the nature of our function. F of z is equals to 1 over z, okay. So so we know at the back of our mind that we cannot write a Taylor series expansion, okay, at this point here. Why? Because it is not defined here. The derivative is actually not going to exist even at that point there. But so what did I want to explain here? Okay, let me see. So we cannot write a Taylor series expansion at this point here, that is at the point z equals to 0. We cannot no Taylor series expansion. What else? Oh yes, however we can have it at any other point, because if you have any other point, maybe z equals to 1, z is equals to 2, z is equals to 3, it is defined, not so. So let us assume that we are going to expand it along z equals to 1 here. So along z equals to 1, okay, so we have that our radius, where our complex number is going to be defined, is defined by this circle here, which is centered at z equals to 1 and has radius 1. So from here to here is 1, so this will be 2, and of course that is 0. Okay, so that is, that is our what? I hope you remember from your study of complex variables when you're writing the locus of a complex variable. So we know it is centered at z is equals to 1, and has radius 1. So in other words, the shaded area here is what we call our radius of convergence, okay? And in this radius of convergence here, you can have a Taylor series expansion in there. You can have a Taylor series expansion at any point inside there, which is shaded. So you can have a Taylor series expansion at any point okay, in R here. So maybe one other thing that I have to say, R is our radius of convergence here, okay, can be defined as the minimum distance, okay, between the nearest, okay, I don't want to say the minimum distance. Our radius of convergence can be defined as the distance between Z naught, okay, and and the singular point, okay, the minimum distance between our Z naught, in this case here, which is Z is equals to 1, we're expanding it around there, until the nearest, okay, the minimum here is going to tell us it is the nearest singular point, and in this case here the nearest singular point is Z equals to 0, ZS. In other words, here our singular point is Z is equals to 0, and then our Z naught, where we're expanding along, is where we're getting our Taylor series expansion, is Z naught equals to 1. So our radius of convergence, the circle which I eventually drew, is defined as the shortest distance between our point, okay, of expansion and the singular point. Of course, when we talk about the shortest distance, we look where we're expanding, and then we look for the next singular point, the shortest distance there, and that is going to be our radius of what? Of convergence. So what else can I explain in here? Okay, maybe it will even get much clearer as we move. Let me finish this by looking at just one more theorem here. So I am sorry, according to the outline, it is quite theoretical. Most of the things given in the outline are quite theoretical, okay? You can look through it yourself and also see. Yeah, but we shall have a few breaks here and there, and we can see how we can maybe put in some computational aspects. So we have our complex number here, our complex valued function rather, okay? F of z is that. So the theorem tells us that if f of z given by that is holomorphic, if it is holomorphic, okay, in a region, if it is holomorphic in a region R, then U and V satisfy Laplace's, U and V satisfy Laplace's, then U and V satisfy Laplace equation in R. Okay, so if that is holomorphic, then they satisfy Laplace equation in R. And what does Laplace equation tell us? That del U squared U equals to 0 and del squared V equals to 0. So that's just the meaning, that if it is holomorphic, then the real and the imaginary functions here, or the real and imaginary parts there, satisfy Laplace's equation. Laplace's equation is given as that. If you're not familiar with this notation, you will find people writing it this way. It will also mean the same, okay? However, most easily we can write this would simply mean the second partial derivative of u, okay, with respect to x squared, okay, plus the second partial derivative of u with respect to y squared equals to 0, and this one here or this one here would simply mean the second partial derivative of v, with respect to x plus the second partial derivative of v with respect to y equals to 0. So this is all we know, that if a function is holomorphic in a region R, then the real part here, we can differentiate it first with respect to the first variable. We can differentiate it twice with respect to the first variable, and then we add the result of differentiating it twice with respect to the second variable. It should give us 0. And also that's this one here, this other part here, when differentiating twice with respect to the first variable plus differentiating it twice with respect to the second variable should give us what? 0. Then some other terminology is that because they satisfy the Laplace equation, the real and imaginary parts of the complex number u and v are considered to be what we call harmonic functions. So why are they harmonic functions? Because they satisfy Laplace equation in R. Okay? Great. So yeah, that is enough for now, and I hope you have enjoyed. Thank you, and we'll see you in the next video.